Of auditory signals. And so what we want to do in this lecture is continue with that. And remember, masking is when you have a stimulus that occurs on top of an existing stimulus and they share a critical frequency band, which then means that once the masking signal gets large enough in intensity, you no longer can hear the stimulus signal that's being masked. So temporal masking is non-simultaneous masking, and I'm pretty sure we went over this at the end of the last lecture. Basically, this is when a stimulus occurs that makes other sounds inaudible, and it either immediately precedes or immediately follows the stimulus. And I think we talked about in the last lecture how if you're watching something like CNN and some reporter says something that is considered not suitable for prime time, they will cover it with a beep. And a lot of times, if it's live, you'll note there's a slight delay. So that would be temporal masking that's occurring in real time. So that's a kind of an application. And I think we ended the lecture saying that basically we shouldn't confuse temporal masking with the ear's acoustic reflex. And just to remind you what that is, that's the pathway that comes from the auditory processing center of the brain back to the hair cells in the ear, causing them to stiffen because of the detection of loud noise, and it's a way of protecting the auditory system. So ipsilateral or same-side masking isn't the only condition where masking takes place. You can also have what is referred to as contralateral masking. So in this case, you might hear the signal in one ear, but deliberately not hear it in the other ear by applying a masker to the other ear. And then finally, when you have central masking, this means a masker just causes a threshold elevation. And this can be in the absence of or in addition to other effects due to interactions within the central nervous system between the separate neural inputs that are obtained from the masker and the signal. So I believe that I discussed this before, although not with this slide, but when you try to mask one signal with another signal, particularly narrowband noise or a sinusoidal tone, if you've got both a sinusoidal signal and a sinusoidal masker, if they're presented simultaneously, you get an envelope of the combined stimulus, and that can fluctuate in a pattern that's known as beats. They occur at a rate that's defined by the differences between the frequencies of the two sounds. If this difference is small, then basically you perceive the sound with sort of like a periodic change of the loudness, almost like amplitude modulation. If these beats are fast, then it sort of sounds like a rough signal. This is actually sometimes done intentionally. If you've ever listened to a lot of choir music in a really good auditory environment, you can sometimes hear this surge in intensity that occurs almost periodically, and that's a beat frequency because there are slight differences in the fundamental frequencies of the different human voices. If the frequency separation is large enough, then you actually can hear two separate tones. So beats can be a cue to the presence of a signal, even when the signal itself is not audible. And the influence of beats can be reduced by using a narrowband noise as opposed to a sinusoidal tone for either the signal or the masker. Now, beats occur in areas outside the auditory range, and you can actually see this in some electromagnetic systems. In fact, I'm looking at something right now that involves that at frequencies that are not within the auditory range, and they're actually not sound waves. So this happens throughout different regimes of the sinusoidal type signals. So there are lots of different mechanisms of making masking. One is suppression. So suppression is when you have a reduction of the response to a signal due to the presence of another. And this happens because the original neural activity caused by the first signal is reduced by the neural activity of the other sound. Combination tones are products of a signal and a masker, and this happens when two sounds interact, causing new sound, which can be actually more audible than the original sound. And this happens because there is some nonlinear distortion that's occurring within the ear. So the combination of the tone of two maskers can actually be a better masker than the two original maskers alone. This is because the sounds interact in different ways, depending on the difference in frequency. So you can have what is referred to as cubic difference tones and quadratic difference tones. So if F1 is the first frequency and F2 is the second, you get this interaction 2F1 minus F2. Quadratic difference is F2 minus F1. And there are a number of these, but these first two are the most common. So multiple tones played at the same time can give you a better masking effect. Off-frequency listening happens when a listener chooses a filter that is just below the signal frequency to improve their auditory performance. So this off-frequency filter reduces the level of the masker more than the signal at the output level of the filter, which means you can hear the signal more clearly, and therefore you get an improvement of auditory performance. And then finally, one thing that I mentioned in a previous lecture was the use of auditory masking in tinnitus maskers. And this is used to suppress these ringing, hissing, or buzzing sounds of tinnitus that's associated with hearing loss. It can also be used in various kinds of audiometry, like pure tones, and the standard hearing test to each ear unilaterally, and to test speech recognition in the presence of partially masking noise. And this is kind of a big one, this last thing, for a lot of reasons, including intelligence reasons, as well as eavesdropping applications, where you're trying to follow a particular person or a particular, you're trying to recognize what someone is saying. And so if you've got masking noise, so think about, trying to talk to the person next to you in a crowded bar or in a football game, or when there's loud car noise or fan noise. Auditory masking is often exploited to perform data compression for sound signals as well. So there are certain times in certain particularly stochastic algorithms where the addition of white noise is useful as far as the functionality of the algorithm. So I would say that auditory masking could also be used in certain signal processing applications not mentioned here. Now, if you want to see a couple of fun videos, so these are people who have provided a couple of video lectures that I think you should watch. One is on this idea of critical bands. One is on auditory masking. These are 15-20 minute videos on YouTube, and I think they're very good videos. The speakers are very good. I vetted these, and I think they give you a good overview of this whole idea of critical bands and auditory masking. I will also say, and it's also not mentioned in this set of lectures, that some of the higher level hearing aids, in other words, higher level equals more expensive, what people are doing is they're actually creating hearing aids that have different properties in different critical bands. So you may, in a certain critical band, you may basically have a greater gain, and in the others, no gain at all. So if someone's hearing loss is limited to a particular band, then the hearing aid may increase the intensity or amplify the intensity in that band only. So that way the people don't hear excessively loud noises at frequencies where their ears are not damaged. So human auditory filters. Now your ear itself and your cochlea and your auditory nerve system basically forms an auditory filter. And so there were some experiments that were done to determine the shape and the bandwidth of human auditory filters. And the following was observed. Okay, once again, the motivation for this is to understand A, how to help people who are hearing impaired, and B, how to best duplicate the environment heard in the human ear for various machine learning, voice recognition, speech synthesis, and other applications. So the bandwidths of these filters increase with the central frequency of the test tone, and the filters are not constant Q. In other words, the ratio of the bandwidth to the center frequency is not a constant. It's going to increase with frequency. They are nearly symmetric, and the attenuation of the band edges is going to be very high. So you can use a 7th order polynomial fitted to each of the curves. And if you do that, you get as a transfer function for the auditory filter, for the power, the equation that's shown here in 5.7, where f sub 0 is the frequency of the filter and alpha is the selectivity. So in other words, as its value increases, so does the width of the filter. So we can look at a graph for various values of alpha. So this is a 3dB bandwidth of the filter shown at 1.29 alpha, and using the integral of the filter function, the curves look a lot like the curves that were shown earlier in the chapter. The variation of 3D bandwidth with frequency was approximated by the equation given in the previous slide. So this is basically just signal level of 76% correct, and this is delta F in kilohertz. The symmetric auditory filter shown in this figure uses 3 different values of alpha, showing that the bandwidth of the filter increases as alpha increases, and this is also that equation that we viewed on the previous slide. And once again, remember that higher frequency auditory filters have a wider bandwidth. So this is just the equation in logarithmic form, and this is the code to generate the plots. So subjectively, the way we define audio signals are in terms of loudness, pitch, and timbre. And these are subjective because this is how we would describe sound, and they're corresponding to sort of certain measurable counterparts, like sound intensity would correspond with loudness, the fundamental frequency would correspond with pitch, and the overtone structure would correspond with frequency. And certain experiments, though, show that it's not so clear. You don't necessarily have this simple one-to-one relationship between these two sets. So we will go to figure 6.1, but point out before we look at that there's a direct relationship between the two sets of characteristics. The dotted lines show the interdependence of all of these terms. So the subjective measure of loudness is directly related to sound intensity, but can also be influenced by frequency and overtone structure. So I have a person in my family who is exceptionally sensitive to very short duration sounds like that of a balloon popping. So it's short duration. It tends to be a very sharp, crackly kind of sound. They don't respond well to drums. And then I have another person, and so she would describe the sound as being very loud when in fact it's actually not loud. It's just the sound that she's particularly disturbed by. I have another person in my family who cannot tolerate fan noise. So even if a fan is turned to a very low level, the fan noise is such an immense distraction, they perceive it as being very loud. And while it may not mask the performance of the hair cell in the ear, it masks the auditory processing system. So when they have this distraction, they cannot process other sounds or conversation. So it would be comparable to if you're trying to locate your cat in a room and there is a very distracting, bright, flashing light. So even though technically you can still see the cat where he's hiding, the light is so overwhelmingly distracting that you perceive that as being much brighter than it is, and you perceive where the cat is as being very dark. So a lot of this is the physiological response of the sensory organ, the eye, the ear, etc. But another part of it is what's going on in your brain. So we will look, here's just, this is just a schematic. It doesn't really say anything other than to say the intensity that you perceive has to do with mostly loudness, but also pitch and timbre. So musicians have worked with this for a long time. And so they have this scale for loudness. If you play the piano and read musical scores, actually play any instrument, read musical scores, you're familiar with this scale of P's, M's, and F's. And so I remember this well. But once again, your somewhat quiet and my somewhat quiet are quite different. And so you don't really, it's a very personal perception. So sound pressure level, sound intensity, phones and sons. Sound pressure is defined as the local pressure derivation from atmospheric pressure. And so the SI units of sound pressure are the same as any kind of pressure. They're the Pascal or newtons per meter squared. Sound intensity, which is also known as acoustic intensity, is the power that passes through a unit area, normal to the direction of the sound wave. And the SI units of sound intensity are watts per square meter. So as the power of the wave is proportional to the amplitude, the sound intensity is proportional to the square of the sound pressure. And the most common measure of sound pressure is a sound characteristic that's called sound pressure level, and it's defined by equation 6.2 here, where P sub 0 is the reference pressure, and that would be approximately equal to the threshold of hearing at 2 kilohertz. So it's defined to be 20 micronewtons per meter squared. So that would be your basic threshold of hearing. So then the sound pressure level is proportional to that on a logarithmic scale. Since sound intensity is proportional to the square of the pressure, then the sound pressure level can be defined as identical to the sound intensity level, which is defined as a ratio between, once again, this sound intensity level versus a reference, which would correspond to this reference pressure level, P sub 0. And note, all done in a logarithmic scale. So two sounds that have the same sound pressure level in dB are usually not perceived as having the same loudness, because there is this issue of equal loudness across the frequency spectrum. So the phone is a frequency equalized measure of loudness that's based on the concept of equal loudness curves. So the equal reference tone is 1 kilohertz. A sound is considered to have a loudness level of L sub n in phones if it's perceived as being as loud as an L sub n dB tone at 1 kilohertz. So the implications of this definition are you can't perceive negative phone values. A phone value of 0 defines the absolute threshold of hearing, and a constant phone value describes an equal loudness curve. So although the phone is a better description of loudness because it's linear, it's not directly proportional to perceptual loudness in terms of level, in which case we look at the Sohn scale. The Sohn scale provides a linear scale of perceptual loudness for all intensities. It's defined to reflect the observation that, first of all, an increase in phone value of 10 is approximately heard as a doubling of perceived loudness, and secondly, the most useful range of phone values for musical and general listening is between 40 and 100. So the Sohn scale is therefore defined as an exponent of 2 within the phone value of 40, giving a Sohn value of 1 of I, 50 giving 2, 60 giving 4, etc. So the relationship between phones and Sohns is basically exponential. So L sub n is the measure of loudness made in phones, and n is the equivalent value in sones. So these are terms that musicians and audio processors use. They're based on, sort of the same fundamental things we base signal processing on, but it's a terminology that's unique to people in sound and audio. So if you look at the relationship between the musical dynamic notation that we're perhaps all more familiar with and phones and sones, this table gives that relationship. So the other subjective measure is pitch and the perception of pitch. So the perception of the pitch of a sound is a complex process. It occurs within auditory perception. For pure tones, the perceived pitch corresponds to and varies with the frequency of the tone. For complex tones, the perceived pitch is a result of this complex analysis of harmonic contents. And remember, it is the human auditory system that is doing this complex analysis, and it does it automatically as a result of years of developmental training and formation of, the neural networks within the brain and synaptic pruning that's occurred. So perception place cues are peaks of excitation that occur along the basilar membrane. And temporal cues have to do with the periodicity of each auditory nerve firing. Variations in pitch will create a sense of melody. So first let's talk about the perception of pitch and place theory. So as we've discussed before, the place theory of pitch perception was that we have this input sound and it stimulates different places on the basilar membrane. And therefore, it activates very specific nerve fibers with characteristic frequency responses. So a single sound can have multiple frequency content. And if it's rich enough in overtones, it's exciting more than one location of the basilar membrane. It's almost like you would have Fourier series components consisting of a fundamental frequency and multiple harmonics that are present, and so you're exciting different filters with different harmonics. For complex tones that have a lot of frequency components, the different maxima will occur along the basilar membrane at positions that correspond to those frequencies. The pitch is assumed to be the position on the basilar membrane with the maximum excitation. But in complex tones, your perceived pitch is not always the lowest frequency component present. So you can have a complicated harmonic sound. The pitch can remain perceptually constant even when its fundamental frequency has been removed. So in other words, you can have both upper and lower harmonics or you can have harmonics that are present. You will still perceive the pitch of the fundamental frequency even if it is not present. So let's talk about this a little bit along with speech. So one of the projects that I'm considering having either a subsection or the entire class do this semester has to do with higher frequency components of speech that are typically not analyzed by audiologists or not considered super important by audiologists. But it turns out that they can be an important feature or biomarker of certain voice characteristics. And it turns out that there's some evidence that we might be able to differentiate speakers almost more accurately by looking at the higher frequency content than by looking at the fundamental frequency content. In fact, audiologists know, for example, that you can take a speech signal and you cannot filter away the fundamental frequency, and the speech can still be understood. The problem then becomes a problem of getting the intensity loud enough and enough power in those upper harmonics. But particularly with things like consonant sounds or hissing type sounds, like S's and Z's that don't have a lot of voiced energy, you can still understand those. So it's kind of interesting that seems a bit counterintuitive. So the perception of speech also has a temporal theory. The temporal theory is based on the rate of neuron firings for the activated auditory nerves on the basilar membrane. So basically the theory is based on phase locking of neural firings, time intervals between successive firings that occur at approximately integer multiples of the period of the waveform. So neural firing intervals are assumed to be measured by the superior olive or in the auditory pathways, and periodicity can be extracted then from autocorrelation. But phase locking does not occur above frequencies of 5 kilohertz, so this doesn't explain the perception of complex tones above this frequency. Sounds that are produced by musical instruments and the human voice and almost all everyday sounds have fundamental frequencies that are less than 5 kilohertz. So what the phase locking means, and I believe I referred to this in an earlier lecture. If not, I can show you, during class a quick view that when you're below 5 kilohertz, the actual ear cell itself will mechanically move, and it moves in phase with the stimulus signal. Above 5 kilohertz, the mechanical properties of the cell will not allow it to oscillate faster than 5 kilohertz. So what it does then is it follows, if you would envision, for example, a very high frequency signal that is maybe like if you were to draw an envelope around that signal. So it starts at 0, it ramps up in intensity, it goes down, draw an envelope, it almost looks like an amplitude modulation. In that case, the hair cells are following the envelope. So it's a different mechanism above 5 kilohertz. Okay, and I think that was all I wanted to talk about. So let's summarize what we've sort of talked about in terms of the human auditory system, and then let's talk a little bit about why this is important for sort of human auditory response and for engineering. So the human system itself has an incredible set of filters given some bandwidths, often called critical bands, and these occur in physical locations along the basilar membrane within the cochlea. The hair cells vibrate or bend primarily in sync with, at least up to 5 kilohertz, the incoming pressure wave and vibrations of the bones that are conveyed to the cochlear membrane. Once those excite the hair cells, the bending of a hair cell causes a pore to open, changing the ions in and out of the cell and resulting in a neuron firing from the hair cell to the auditory nerve. The auditory nerve, then different neurons within the auditory nerve tract get excited depending on their physical location. And they get excited and fire at a rate that helps interpret what the incoming sound is. If the sound is multi-frequency, then you'll get multiple auditory nerves. And there is also time syncing. So if the frequency is changing, the auditory nerves that are excited are changing. It's then all sort of in a time frequency filter within the auditory processing system, then deconvolved and interpreted as sound. And then the person responds to whatever the sound is. So it's a very complex signal processing. It's nonlinear, it's time frequency based, and it's also spatially distributed. So given that, if you now as an engineer want to start processing speech, in order to process speech for human application, then you have to understand how the human brain processes the speech. And you would like to build your filter banks, and it doesn't matter whether you're trying to do transmission or recording or filtering. You want to build your filter sets to somewhat align or match with the human hearing system. Now, this all becomes less relevant if you're talking about some other auditory environment. So in the documentary that I asked you to watch last week, part of what the documentary discussed is the sounds that occur in these ecosystem environments. And so the members of the ecosystem community, who are primarily not human, evolved to exist in this auditory environment, and they respond to it, physically and in every possible way. If you remove that, then certain cues that they follow that are auditory are missing, which threatens the ecosystem as far as species being able to find food, being able to find shelter, being able to sense where water is located, and things like that. So what we're talking about in this class is primarily responding to the needs of the human auditory system, at least for the next 3 weeks. So what we want to look at next, and where we're going to go next, is we want to look at what are these features of human speech from the perspective that we're wanting to process them, recognize them, synthesize them for human consumption or human interpretation. And so even our machine learning systems and our natural language processing systems are aligned with the human speech and auditory system. So that's why we've spent all this time talking about the ear, talking about sound, talking about biofilters and bio-inspired filter banks, so that we understand that in creating products for commercial, military, whatever kind of applications, that's the driving sort of design criteria, at least for what we're doing. And that concludes this part of the lecture.